Okay, so we're going to kind of cover, I guess, kind of the surface level of a lot of stuff today. We're going to kind of touch on the basics of a lot of different things and try to make some sense of it. Okay, so the overarching concept that we're looking at today is we're looking at different information that can be provided to us through a scatter plot. Okay, so a scatter plot which I'm sure most of you are hopefully familiar with. Well, I guess I should make that plural, right, to fit the sentence. Scatter plots are used to visualize the relationship between two numerical variables. They are used to analyze data and look for potential relationships. Okay, so scatter plots are generally not linear. They do not form a straight line, but we can look for general patterns and try to look for a general linear relationship between data, so that we are able to then use that data to predict. Like if I wanted to look at general trends for the entire student population of Noblesville High School, okay, it's not plausible for me. So as we talked about last time with sampling methods, it is not plausible for me to survey every single student. Okay, I understand with technology like Canvas and different things like that, it gets a little bit easier. But if I want to sample students rather than survey every single student, I can create a scatter plot and look for general trends. Obviously, the more data that I collect, the better that my trend data will be, the more accurate that my trend data will be. But we work with what we have, okay? So we want to consider these following three scatter plots, okay? So looking at scatter plot 1, 2, and 3. I want you guys to go ahead and answer questions 1, 2, and 3 together with your groups. Go ahead. So 1, 2, and 3 together with your groups. Go. All right, guys, so number 1, does there appear to be a relationship between X and Y?
There does.
There does?
It does.
Okay. What kind of relationship are we seeing? Okay, I heard a word over here, positive. Why do you think it's a positive relationship?
It's going up.
Yeah, in general, it's going up left to right, correct? So we could draw something called a line of best fit to show the general relationship. It would be something like that, right? So my general relationship is positive. It does seem to form a straight line. So that's good there. What about number 2? Does there appear to be a relationship between the data in scatter plot 2? You guys don't think so?
It looks like it's kind of going down and then back up.
It does. It kind of appears that it's going down and back up. So I would not say that there is a linear relationship between the data, but we could kind of see that there's somewhat of a relationship. On that one, it would probably be the best idea to gather some more data before we tried to make a conclusion about that one, because there aren't a whole lot of points. Okay. What about scatter plot 3? Does there appear to be a relationship there? No, there doesn't, really. I mean, you can see that we have quite a bit of data. It doesn't really seem to be following any kind of specific pattern. You kind of have numbers all over or dots all over the place, and I couldn't really tell you if that was positive, negative, anything like that. Okay, so we can look at scatter plots and see relationships. So there is a summary statistic that we use called the correlation coefficient. So a correlation coefficient is a summary statistic used to describe strength and direction of a linear relationship. Okay, this correlation coefficient is often represented with the letter R. So if you ever see R equals, that's how you know you're looking at the correlation coefficient. Okay. So again, it not only can tell us things about the strength of a relationship, so how strong the correlation or relationship is, but it also tells us if it's a positive or negative relationship, okay? And we're going to kind of explore some graphs and try to match the graphs with some correlation coefficients to kind of see what we're looking at here. So let's go ahead to the next page. Okay, so what I want you guys to do is I want you to do number 4 and 5, A and B. Okay, so you're doing this entire page. So you're doing number 4, which number 4 just has you match each one of these scatter plots to one of the relationships down here. Now, obviously, you don't know much about this R number over here yet. That's what we're kind of trying to discover. But I am going to match the words with one of the graphs. So A says it is a very strong relationship and it is positive. So which graph do you feel like is the strongest positive relationship? 7. 7 would probably be the strongest. Why do we consider that to be the strongest? Yeah, we think, Nico or Paul, sorry.
Because the dots are more closely aligned.
Yeah, the dots are very close together, right? That would represent a strong positive relationship. Okay, so we would say scatter plot 7. Okay, ooh, what'd I do? Okay, so that would represent scatter plot 7. So I want you to go through and match the rest of them with their statements. Once you match them with the statements, then you're going to kind of look at the correlation coefficient that we have. So a strong positive relationship has a correlation coefficient of 0.981. Okay, so that's what that particular strong positive relationship had a correlation coefficient of. Once you do that and you kind of analyze the numbers, then you're going to kind of try to answer 5, A and B, describing what we can determine about a correlation coefficient. Okay? All right, go ahead and do that with your groups. Okay. All right, so a relatively strong positive relationship. So we're backing off of the dots being so close. So which one would match that? 2. 2? Oh, yeah, 2. I was looking at the wrong labels. Okay. Yes. Number 2 has a positive relationship that is relatively strong. How about a relatively weak positive relationship? 4? Yeah, I'd say that's about right. Because in general it's kind of going up, but it's pretty weak. How about no linear relationship? 3. Wait, 3? Or 6? Yeah, I'd say 3 is probably. Yeah, I'd say you guys are right. 3 is probably a little bit more no relationship than 6 is. So then a relatively weak negative linear relationship. So that would be 6, right? So what's the difference between a positive relationship and a negative relationship as far as our correlation coefficient goes? Yep.
The positives go up to the right corner, the negatives go down to the left corner.
Good. So that would be with our graphs. What about with the correlation coefficients? Yep.
The more positive they are, the higher the numbers are, and the more negative they are, the lower the numbers are.
Okay, but all of the negative relationships have what kind of correlation coefficients? They're all negative, right? So that is a pretty simple thing to figure out. If the relationship is positive, it's a positive number correlation coefficient. If the relationship is negative, it's a negative correlation coefficient. Okay, so then we get to a stronger negative correlation. That would be graph 1, right? And then our strongest negative correlation would be 5. Okay, so as Laney said, I guess we just kind of determined together, right, that positive is positive, negative is negative. Okay, so a positive correlation or a positive relationship gives a positive number, negative correlation gives a negative number. The strength, okay, so if it's stronger, is it closer to 0 or further away from 0? If it's stronger, it's further away. So stronger is close to 1, right? Closer to 1 or negative 1. Okay, so the stronger relationships are closer to 1 or negative 1. the weaker it is, the closer to 0. Okay? So if you had a correlation coefficient of negative 0.75, that would be a negative relationship, and it's relatively strong, right? If you had a correlation coefficient of 0.18, that would be a very weak correlation, right? Because it's closer to 0, and it would be positive because it's a positive number, okay? So what you have to be able to do, because later on, we're going to look at actually finding the correlation coefficient and interpreting it. Finding it is really easy because we're going to use Desmos to do that, okay? So we'll use our graphing calculator to find the correlation coefficient, but you have to be able to tell me what that means. So if you see 0.75, you have to be able to say that is a positive, strong relationship, okay? All right, let's go to the next page here. Okay, just one thing I want to cover really quick. It is important to recognize that correlation does not mean causation, okay? Just because two things are correlated does not mean one causes the other. That would be like saying that wearing shorts causes ice cream sales to go up. Okay, would people wearing shorts and increased ice cream sales correlate? Would they have any kind of relationship? What happens when you're wearing shorts? It's warmer outside. And what happens when it's warmer outside? Generally, people eat more ice cream. So there may be a positive relationship between those, but does that mean wearing shorts causes ice cream sales to go up? No, it doesn't. So that's what I'm saying. Correlation does not necessarily mean causation. So let's read through number 6 just together really quick. The number of fire trucks showing up to a scene and the damage to the structure have a positive correlation. Right? So generally with bigger fires that cause more damage, they're going to send more fire trucks. But that does not mean that more fire trucks cause more damage. Okay? The number of drownings at beaches and ice cream sales have a positive correlation. Okay? Ice cream does not cause people to drown. Just more people are in the water because it's warm. Right? Shoe size and reading ability have a positive correlation. So should parents buy bigger shoes to help their children read? That's not necessarily true. I'm not necessarily saying shoe size and reading ability have a positive correlation, but if we had a study that said that, it definitely doesn't cause causation. Okay. All right. So let's go ahead. We already kind of talked about 7, so let's just move on from that. And let's look at line of best fit, or the trend line, okay? So the line of best fit, which I just like to abbreviate it, line of best fit, okay? A line of best fit, or you could say a trend line, is a line that best represents the relationship of data on a scatter plot. The equation of this line is very useful for predicting future data. Okay, so the scatter plots below show a linear relationship. Go ahead and with your groups, I want you guys to draw your own line of best fit on each of those graphs. Draw your own line of best fit on each of those graphs. Go ahead. Okay, so look up on my screen really quick. For scatter plot 1, would this be a good trend line? No, why not? Yeah. So my line is positive. The data generally shows a negative relationship, so that's definitely not good, right? Is this a good line of best fit? I did negative, but it doesn't follow the general pattern, right? Is this a good line of best fit? I followed the general pattern. It's negative, but it's above almost all of the data, right? So I want to follow the same general pattern as the data, and I want to put it I want to try to put it about where there's an equal number of points on top and bottom. That's your best line of best fit. Okay? So for scatter plot 2, it is a positive relationship, and I want to go kind of in the middle, have almost the same number of points on top and on bottom. Scatter plots like 3 and 4 get a little more tricky, right? In general, would you say the data on scatter plot 3 is in a positive relationship or negative relationship? Or just like no relationship at all?
When you look at the top of it,
It looks a little bit more negative.
It might look a little bit more negative, but when I see like all these points down here grouped together, it almost looks pretty flat. I would say there's no correlation on this. But if I had to draw a line, let's see, I would actually say it looks a little more positive than negative. That line might be a little bit low. I don't know, that's a tough one. But drawing trend lines on stuff that doesn't have a very good correlation is challenging. Okay, 4 is a little more clear that it is a positive relationship, and I kind of want to go in between. But definitely 3 and 4, would you say those are stronger relationships or weaker relationships? Those are definitely weaker, right? So my correlation coefficient on those would be much closer to 0. Okay, so we've talked about correlation coefficients. We've talked about scatter plots. Let's move here. So we talked about 9 already. We want same shape or same direction. We want equal points above and below. Okay, so we want it to be in the same direction as the relationship, and we want equal points above and below. It's not an exact science. You don't have to have the exact same number on top and bottom. You just want it to be close. Okay. Okay. So let's look at how the line of best fit helps us. So consider that scatter plot 4 above represents the age and shoe size of children. So the equation of the line of best fit is y equals 2/3 x plus 1. So all of the lines of best fit that we'll have will be in slope-intercept form. Okay? And if you remember back to slope-intercept form, that's y equals mx plus b, where that m is the slope, and that b is the y-intercept. Okay, so y equals mx plus b, where m is the slope and b is the y-intercept. So we want to be able to describe what the slope and y-intercept mean in context of this problem. Okay, so what does a y-intercept of 1 mean in terms of this problem? If we're talking about x is age and y is shoe size. Okay, that would be the mathematical interpretation, right? It crosses the y-axis at 1. But in context of our problem, what does it mean? So if the graph starts at 1, what does that mean in terms of age and shoe size?
We don't have kids. They start at 1.
They start at 1. So when they're born, generally kids start with a shoe size of 1. That's what that would mean. Okay? So for b equals 1, we would say children are generally born with size 1 feet or something along those lines. Okay, so that's for my y-intercept. Oh man, this is gonna... I'm going to run out of room, aren't I? Okay. What about the slope? The slope of 2/3. Yep.
The rate at which their feet grow.
Yeah, that's the rate at which their feet grow. So for every year that they are older, what's going to happen to their feet? It's going to be 2/3 of a size bigger, right? So then we would say, sorry, I'm going to pull it over here. This is still in, so m equals 2/3 is going to tell us for every year older, their feet grow 2/3 of a size. Okay? And to be honest, the slope one is the one that I'm more worried about. Okay? We won't really describe the y-intercepts very much. We'll be describing the slopes most of the time. Okay? And it's that simple. Whatever your x value is and whatever your x and y values are representing, you're just going to say for every this, that's going to happen based on your slope. Okay? So the best thing that lines of best fits are good for is predicting. So let's predict the shoe size of a child when they turn age 6. So age 6, is that an x value or a y value? It's an x value, right? Because it tells us up in the problem that age is x. So I'm going to use my line of best fit. Y equals 2/3 times the age, which we know is 6, plus 1. So remember, a fraction times a whole number, multiply the tops, divide by the bottom. So 2 times 6 would be 12. 12 divided by 3 would be 4. So we have y equals 4 plus 1. So we would say it's going to be size 5. So when they're age 6, they would have a size 5 shoe. Okay, and why would this data and equation be useful would this data and equation be useful to predict the shoe size of an adult age 40? Why or why not? Talk about that really quick in your groups. Would it be useful, with this data and line, be useful to predict the shoe size of an adult age 40? Okay, guys, talk to me. Would this be useful? No. Okay, that's good that we came up with no. Can we say some reasons why or why not? Yes.
Just thinking of it, there are different types of shoes for adults.
Well, what happens as you get older, as you turn into an adult? What happens to your shoe size? Yeah.
Your feet stop growing.
Yeah, your feet stop growing. Luckily, because I would have like size 500s by now, right? So your shoe grows a lot when you're a child, and then it kind of slows down after that. Also, if you're thinking about our data, okay, it's not useful to collect a bunch of data about people ages 0 through 5 and then try to predict what a 40-year-old's going to have based on that data, okay? Yes, it is good for predicting data that is close after the data that you've collected, but if you get too far out from the data you collected, it becomes obsolete, okay? So you don't want to collect a bunch of data based on 0 to 5-year-olds and then try to extend that data out to somebody that's 40 or 50 years old. 20, maybe. 15, definitely. Okay? 40, 50, probably not. Okay? All right, so now we're into the nitty-gritty. Okay, this is when we're going to use Desmos. So for people watching this video, for people watching the video notes, I'm going to have to kind of switch back and forth between Desmos, so the video might get a little bit choppy here. Okay, so we have this data set, and we want to look at some different information. Okay, so we have bicycle helmets, we have the price in dollars, and we have the quality rating. Okay, so we have the price in dollars and we have the quality rating. So I'm going to freeze this on the screen. Actually, no, I'm not going to be able to do that, am I? Okay, I'm going to go ahead and pause the video here because I got to show some Desmos stuff. So we are currently putting all of the data into Desmos, into a table in Desmos. We're going to talk about price as being the X and the quality rating as being the Y. So I want you to put all of those points into Desmos. Oh, I froze the screen, didn't I? So price is X, quality rating is Y. So I want you to put all of those data points into Desmos, and then we'll kind of group back up here together. Okay, go ahead. Okay, so we just did some stuff on Desmos. And guys, if you want to put this in your notes so that you remember it, you might want to do that. So remember on Desmos. Okay, so on Desmos, you want Y1, the little approximation symbol, right? We don't want the actual equal sign. So the approximation symbol, M, X1 plus B. Okay, so on Desmos, that's what you're going to type in. After you put in your table of data, it'll set it up as X1 and Y1. So you want Y1 is approximately MX1 plus B. And then underneath that, it will list R equals a number, M equals a number, and B equals a number, right? And that is all of the information that we need for our information that we want. Okay, so let's go to the next page and look. Okay, so it says using Desmos on another graphing calculator, which we already did. Enter the data from the table. We did. What's the correlation coefficient? So on Desmos, it told us that the correlation coefficient was 0.030. Okay, I'll give you a quick 30 seconds to talk about what that correlation coefficient implies. So you want to talk in your groups about, is it a positive or negative relationship? Is it a weak? Oh man, I put that in wrong, didn't I? It's 303, not 030. 3. Sorry, I copied it down wrong. So you want to talk in your groups, is it a positive or negative relationship? Is it a weak or a strong relationship? Go ahead. Okay, is it a positive relationship or negative? Positive, right? Because it's a positive number, so relationship is positive. And then is it a weak or strong relationship? It's pretty weak, right? Because it's closer to 0 than it is to 1. Okay, so and weak. Or I guess if you wanted to put it a little more eloquently, you could say the relationship is weak, it's a weak positive relationship. I don't know, whatever. Okay, the equation of the line of best fit. So remember, the equation is y equals mx plus b. So we have y equals, what's the m from Desmos? 0.31, so 0.31 x plus b. And the b is 39.58. Okay, so it says, what does the slope of the equation mean in context of the problem? So the slope is 0.31. So let's go back to, I'm gonna go back to the last page. Actually, if I go back to the last page, it's gonna mess up my video. So you guys scroll back up to the last page. What's the context of what we're looking at? What's X and Y represent here?
X is the price and Y is the quality.
Good. So X is the price, Y is the quality rating. So if X is the price and Y is the quality rating, what does a 0.31 slope mean? So do your if-then statement. For every
X is the quality rating, Y is price.
oh. Oops. Well, I kind of messed up, didn't I? I told you guys that X was the price and Y was the quality rating, but then in the graph on the notes, it flips those around. That's all right. We'll just roll with what we've been doing. So we'll just say X is the price and Y is the quality rating. So for every $1 that we spend, what's going to happen? Quality is going to go up 0.31. Okay? So we would say for every dollar spent the quality increases by 0.31. Okay? So for every dollar spent, the quality increases by 0.31. Okay? And then we want to predict what the quality rating for a $75 helmet would be. So if we put $75 in for X, then we have Y equals 0.31, $75 in for the helmet, plus 39.58. Okay? Somebody want to help me out with your calculator? 75 times 0.31. 23.25 plus 39.58. So Y would be what? 62.83. So the rating would be a 62.83 rating on the safety scale. I think it was 0 was the worst, 100 is the best, right? So that's a higher mid-grade helmet, right? As far as safety goes, that's a higher mid-grade helmet for $75. Okay?